So this converges, right?
I have a question.
Yes.
Because there was the other one where it was the alternating and one -1 to the end diverges. It looks to me like it's still kind of going that way, but it's kind of
It's funneling in.
like are they going from both sides approaching 0?
Yeah, like here's 0, they're going like this.
Okay.
If that makes sense. Funneling in like that. They never reach 0, right? But that's okay, because limits, you don't have to reach it. You just have to get closer to it. All right, so let's try and put it all together. If you have a sequence, okay, so the final summary here. If a sub n equals r to the n, with r an element of the real numbers, okay, so r is a real number, then we have the following. The limit as n goes to infinity of r to the n is going to basically, I'll say equals. It's going to either converge or diverge, right? It's going to converge or it's going to diverge. When does it converge? So converged if r was -1, including -1 or no? It was if r was bigger than -1 and smaller than or equal to 1. Right? Because when it was 1, it was just 1, 1, 1, 1, 1, 1, 1. So that converged. If it was 0, it converged. If it was between 0 and 1, it converged. If it was between -1 and 0, it converged. So that's when it converges. When does it diverge? The opposite of this, right? So if r is greater than 1 or less than or equal to -1. Because remember, if it is -1, then it's gonna diverge, right? Another thing we could put here instead of this, right? If we didn't want to write that, we'd say it converges if r is in here, right? Which is really like this interval. Right? If r is in this interval, then it converges. We could just put here else. Okay, that's more of a computer science term. It's just like, okay, any other thing that happens, it's going to do this. Okay, I'm going to give you another sequence. A sub n is equal to this sequence. Root 2, root 2 root 2, root 2 root 2 root 2, root 2 root 2 root 2 root 2. I think you get the idea. Okay, so does this converge or diverge? Converge or diverge? So before we actually tackle this, let me give you a little bit, and maybe we're still just building up right now to lead us into 8.2. 8.2 is called series. So we're going to go from sequences to series. In order to do series, we have to have a decent grasp of sequences. Most of the problems that you're going to do are going to be problems where the only question is, does this series, which we haven't talked about, does this series converge or diverge? That's the question. And so the answer is like yes or no. Like it either converges or diverges. Getting to that answer requires that you show it, okay? And it's not it's kind of like when we were doing integration, when you'd be given an integral and you weren't quite sure what technique to use. Series is just kind of the same thing in the sense that you're trying to just show if it converges or diverges, but the techniques you use to show it one way or the other is kind of up to you to figure out what to use. And we're going to have all these different tests that we go through and stuff, but this right here I think is a good example of us leading into this. Like, it's a simple question. And if you just put converge as your answer with no justification, you get no credit. Like, even if it does converge, I'm not asking you to just flip a coin. I'm asking you to justify your answer. So you must have justification for your work. It's really hard to grade the stuff from chapter 8 because you could have a whole page of stuff written, and at the end you have the correct answer, converges. But all of your steps have to make logical sense. You can't make any mistakes in terms of your logic. And I think that's what makes chapter 8 difficult, is because it's really one of the first times that you actually have to write your thoughts line by line, and you can't miss anything. You can't assume that n was positive. You have to always think about, these different cases. You have to just cover everything, if that makes any sense. You'll see when we get there, but I think that's what makes it challenging. So for those of you who can't write cleanly and neatly, you're going to need to work on that, because I need to be able to read your work. You can't be like, oh, I just do in my head. You have to be able to communicate your work. Okay, I've been yapping. Yeah, there it is. So maybe first we can figure out what it is they're asking. We're trying to figure out the limit as n goes to infinity of this, right? What's the problem, though? I mean, like, what's wrong with this, the way it's presented to us? Yeah, we don't have like the formula for the sequence, right? We don't have that a sub n equals blah, blah, blah that generates this sequence. We have the sequence written for us, but we don't have the formula. So, any ideas on how we might be able to get to a formula? How about we just start writing out what this is, okay? Like this first one, this is really 2 to the half power, right? That's what that really means. Okay, comma, what is this next one? Well, that's the square root. Well, let me not do the square root. Let me do it this way. This is 2 times 2 to the half to the half. Isn't that what that is? Because 2, square root of 2 is this, and then the whole thing under a root is that. Now, can you put those together? What's 2 times 2 to the half? 2 to the 3 halves, right? So this is really 2 to the half, comma, 2 to the 3 halves to the half, right? That's what 2 to the 3 halves, still raised to the half. And then what is that? 3/4. So this is 2 to the half, and then this one is 2 to the 3/4. Y'all follow that? Okay. Let's see what the next one is. So this one is going to be to the half, right? And then we have 2, right? So that's the square root is this half. This 2 is this 2. And then what's this? What's that? Well, that's this one, right? And that's 2 to the 3/4, right? So this is 2 to the 3/4. And if I put the 2 times 2 to the 3/4 together, what would that be? 2 to the 7/4, right? But then to the half. So that's really 2 to the 7/8. Well, it's kind of fun now. No? Maybe. Okay, let's see if we can get the next one. We have, again, a big square root. That's this thing right here. We have a 2 in front. And then what's this piece? That's what we got from the previous answer. So that's 2 to the 7/8. And if I put 2 times 2 to the 7/8 together, I get 2 to the 15/8. And if I raise that to the half, I get 2 to the 15/16, comma. Let's see, can we predict the next one? Uh-oh.
Yeah, it should be 32 in the denominator.
So we're just going purely off of the prediction from a pattern here.
31 32s.
31 32. What would the next one be? 63 64. So the pattern is that all the denominators are powers of 2, aren't they? 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. And what are the numerators?
Just that minus 1.
That minus 1. Just, right? 2, 1, 3, 4, 7, 8. Sorry, 8, 7, 16, 15, 32, 31. Yeah? Okay. So now maybe we can come up with a formula. A sub n should be equal to 2. So these are all 2's raised to powers, right? Let's do the denominators. How do we generate the formula that would give us 2, 4, 8, 16, 32, 64? 2 raised to the n, right? 2 raised to the n. Right?
What about 2 multiplied with the n?
2 times n wouldn't work because that would give you 2, 4, 6, 8, 10, 12, 14, 16, right? Do you all see that? These are powers of 2, not multiples of 2. Now, what about the numerator? It's that same formula, but just subtract 1 from it. So I'm going to put 2 to the n minus 1. Be careful. Do not put 2 to the n with a minus 1 up there, because that's not the same thing. Right? The minus 1 has to be here. So do you all agree that's the formula? Yep. It ain't pretty, but that's it. All right. Now, does it converge or diverge? So what we need to do now is this. We need to take the limit as n goes to infinity of 2 to the 2n minus 1 over 2 to the n. Right? That's what we need to do. As n goes to infinity, let's see what happens. This just stays here, right? The top goes to infinity. The bottom goes to infinity. So I have infinity over infinity, don't I? But I'm just focusing on this part right here, right? That's going to infinity over infinity. So over here on the side, I'm going to say to myself, let f of n equal 2 to the n minus 1 over 2 to the n on the interval 1 to infinity. I'm doing that because I'm about to use L'Hopital. But I have to first define this thing as a function, a continuous function on the interval 1 to infinity. Now, I'm not worried about the 2, because whatever this power goes to, I will raise 2 to that power, whatever it is. But I'm just focusing my attention on this piece, right? So now, can I bring in L'Hopital? Yes? So the limit, I'm going to go ahead and just go right to it. This is equal to the limit as n goes to infinity with L'Hopital. What is the derivative of 2 to the n? The derivative of 2 to the n is 2 to the n times natural log 2. Go back to Cal 1. Derivative of a to the x is a to the x times natural log a. Exponential functions, the derivative of an exponential function is like this. So I did derivative of a to the x basically is a to the x itself times natural log of a. That look familiar? Now that I've done it? Okay, minus derivative of 1, which is 0. And then you take derivative of the bottom, which is, same thing, 2 to the n natural log 2. And that's just 1, isn't it? That's just 1. So that's headed to 1. If you didn't want to use L'Hopital, you actually could have done this a different way, which is actually pretty clean, is you could have rewritten this like this. Split this up into 2 fractions. Do 2 to the n over 2 to the n. What would that be? 1 minus, then do 1 over that. It's easier to see it, I think, that way. as n goes to infinity, I'm missing the 2 down there, sorry. 2 raised to the 1 minus 1 over 2 to the n. So as n goes to infinity, that goes to 0. You just get 1 minus 0 is just 1. So the answer is going to be, we know the exponent's headed to 1, right? So what's our answer? 2. That sequence is headed to 2. It converges. It converges to 2. All right. Okay, I think I'm almost done. No, I'm not. God, this section just drags on so long. Okay, this will be the last one. There we go. How does this feel so far? I told you chapter 8 is weird because it's different, right? It's like first time exposure for most. So the question is, does this converge or diverge? Right? Does it converge or diverge? What's the numerator headed to? Infinity? How about the denominator? Infinity to the infinity. Right? It's headed to infinity. So you have infinity over infinity. So you might be thinking L'Hopital, but why are you going to throw L'Hopital out? Factorial. So L'Hopital's off the table. You cannot turn this into a continuous function. So what saved us last time when we had that L'Hopital off the table? We were able to somehow use the factorial against itself, right? On the top and bottom, kind of peel off and get them to cancel. Not going to happen. Do y'all see it? It's not going to happen. Because you don't have a factorial on the bottom, right? So we have a problem here. That we can't really go after this the way that we have. So last class, I talked about this thing called the bounded monotonic sequence theorem. Look at your notes from last time. Last time we said that if a sequence is bounded and monotonic, it converges. Now, it doesn't tell you where it converges to. Okay, it converges, but it doesn't tell you where. Right here, I'm just going to ask you, does this converge or does it diverge? I don't want to know necessarily what it converges to. I just want to know if it converges or diverges. So this theorem is actually there for us if we need it. It says if our sequence is bounded and monotonic, then it must converge. So now I have to go about trying to show that this is both bounded and monotonic. So what I was just saying to you a minute ago about this is where in your exams and stuff you have to actually logically explain and show what you're supposed to show. This is your first kind of example of that. Okay, so I want to show, so watch the way I write this. I want to show 1. A sub n is bounded. 2. A sub n is monotonic. Right? Those are the two things I want to show. Now from here on out, you will not see me write want to show anymore. I'm going to write WTS, not WTF. WTS. I want to show. And I actually won't write I either. I'm just going to say want to show. And this is a good habit to get into when you're trying to show something like this. Write down what it is that you have to do first. If you can establish these two things, right, then we'll be able to use the theorem. So let's start with the bounded. So for part 1, A sub n bounded. What does it mean? What do I have to show in order to show that it's bounded? There exists some m that's greater than it all the time, and then some other little m that's always smaller than it all the time. So can you just, by looking at this, and it might have been worth it for us to actually write out the first few numbers in this sequence. Maybe we should write them out so that we see them. Yeah, I'll put it up here. What are the first few numbers in this sequence? So plug in 1. What's 1 factorial? 1 over 1 to the 1 is 1. Okay, so our first number is 1. What about 2? 2 factorial is 2 times 1 over 2 to the 2, which is 4, right? Next one. 3 factorial, which is 3 times 2 times 1, which is 6, over 3 to the 3, which is 27, right? Dot, 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 and we can keep going. So let's see. To show it's bounded, right? First, I want to show a sub n is bounded above. Okay, so I first want to show that it's bounded above. What does it mean to be bounded above? There's some number that's bigger than every number in that sequence. So what number do you want to go with? 2. Would you all agree 2 looks like it's going to be bigger than that? But we need to show it. Okay? I want to show that it's bounded above. Let capital M be equal to 2. Must show a sub n is less than or equal to capital M for all n. So what I'm saying is, look, I'm going to choose 2 to be this upper bound. And now what I have to show you is that my sequence is always smaller than that number for any n you ever plug in. All right? For any n. So let's check this inequality. Is this true? So what's my sequence? N factorial over n to the n. Is that smaller than or equal to 2? Question. This is a question. You can't just state that. You have to actually show that's true. Is it true? Is that always true? I mean, you can tell from here it is, but we need to show it. Do you understand what I'm doing? I know this all looks weird because of the way I'm writing everything on the board, but...
Can you explain a little bit, just real quick, how you got from n factorial over n to the n is less than or equal to 2? Is that based on the sequence?
The sequence, we look and we see this is 1, this is a half. These numbers are getting smaller.
Yeah.
So it's safe to say that the number 2 is above every number in this sequence.
I see.
Okay, so we pick that and we say, okay, this looks like an upper bound, right? That's bounded above. So 2 looks like an upper bound. We just need to show algebraically that this inequality holds all the time for all n's. Okay, so here's the way I'm going to show it. You ready? This is going to be pretty clever. Watch. N times n minus 1 times n minus 2 times dot, 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 all the way down to 1. That's n factorial, right? On the bottom, that's n times n times n times n, dot, 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 all the way down. Right? N to the n is n times. So this, in the n factorial, right? Like if you were to write 4 factorial, that's 4 times 3 times 2 times 1. How many factors do I have here? I have 4 factors, right? If this was 5 factorial, I have 5 factors. If it's n factorial, how many factors do I have? N of them, right? I have n factors. And on the bottom, I have n n's. So would you all agree that that over that, that's 1, right? And I'm trying to show this is true. This is like a question. Is this true? So that's going to be 1. Okay, this right here, what can you tell me about that number? Whatever it is, it's what? Smaller or bigger or smaller than 1?
Smaller.
Smaller than 1. Because the denominator is bigger than the numerator, right? So this number right here is 1 times, I'm going to put a number, I'm going to put this, it's not going to make a whole lot of sense, a number that's smaller than 1. Okay, that's what the next one is. Yes? What about the next one? N minus 2 over n. Smaller than 1. Right? And then what can you tell me about all of these numbers? They're all smaller than 1, right? All the way down. These are all smaller than 1. Is that less than or equal to 2? Yeah. Look, if you take a number 1 and you multiply a number that's smaller than 1 times another number that's smaller than 1 times another number that's smaller than 1, and you keep doing that, it's definitely got to be smaller than 2. Do you all agree with that? Okay, another way you could do this if you didn't like that is you could have multiplied this whole denominator on the other side, and then you could compare them left and right. It would have looked like this. n minus 1, n minus 2, dot, 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 all the way down to 1, less than or equal to 2, n, dot, 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 all the way to n. So we'd have this inequality instead. And what you can see here is these n's cancel, and then you could compare it again, like this n minus 1 smaller than that, this n minus 2 smaller than that, this next one is smaller than that one, and then 1 is definitely smaller than n. So eventually what you can see is that the left side is smaller than the right side. But you have to show it. Yes?
Does it matter where we set the boundary? Like technically
Anything bigger.
than 1 to 2.
1 would have worked also.
But it's the first one is 1.
I know, but your upper bound can be equal to it. So we could have technically used 1, but I'm glad we used 2 because it's obviously above it, right?
So if we chose 10.
10 would have worked. We just have to find any bound that is above it, anything, and that it stays above it the whole time. Now have we shown it's bounded?
No.
We're halfway there. We have to now show it's bounded below. Okay, so next thing, still in step 1. Okay, so this part we're done with. Okay, now I want to show a sub n is bounded below. Below. So I need to get a number that's smaller, right, than all those. What's a good candidate? -1 would work. -2 would work. 0 would work too. And 0 is usually really nice to work with whenever you have an inequality or an equation. So I'm going to say let little m be equal to 0. Must show a sub n is bigger than or equal to 0 for all little n's. This one's going to be pretty trivial. Why is this one going to be trivial? N factorial over n to the n, is that greater or equal to 0 question mark? Why? What's the logic behind this? They're all positive. The n is positive, right? What does n start with? 1, and then it's 2, then it's 3. So if I have a positive number here, I'm going to get a positive here and a positive here, and left side's positive, that's bigger than or equal to 0, true. Yes? For all. This means for all. For all n. Yes?
On the bounded above, you did n.
A capital M?
No, but A7, yeah, there's, and then on the bottom you did 0 instead of the.
Oh yeah, I did. Well, yeah, I did. This should be little m, but it is. I let it be.
But does it matter if you put 2 or 0 and big N and little n?
No, because see, right, this inequality right here really means a sub n is less than or equal to 2, because I have established what capital M is. Here, I established what capital M is, and I'm just stating what it means to say it's bounded below. Okay, are we bounded? So you can just say that's positive number over a positive number, that's definitely greater than or equal to 0, check, right? So are we bounded? Yes. Okay, we're bounded. Now we need to show it's monotonic. So what does it mean to be monotonic? You're either increasing or decreasing. Your sequence is either getting bigger as you go across or it's getting smaller. So we look at it. What is it doing? Looks like it's getting smaller, right? Starts out at 1, then it goes to 2, then it goes to 6 over 27. So for my second thing to establish this, number 2, a sub n monotonic, by inspection, it looks like it's decreasing, right? So I want to show a sub n is decreasing. And I realize you can just look up there right now and tell it's decreasing, but you still have to show it. Because some sequences, believe it or not, some sequences will actually decrease, and then all of a sudden they'll turn around and start increasing. So you have to show that it's decreasing. So what does it mean to be decreasing? That means a sub n will be bigger than or equal to a sub n plus 1 for all n. Now we talked about this last class.
Wouldn't it just be bigger than not equal to?
Well, we talked about that last class too, right? It was a strict, it was strict, it was strict, it was strict. We couldn't have a constant, that's right. Yeah, strictly decreasing. Yes?
So you just said that
Not necessarily. You could have a sequence that's defined to be like a parabola, where in the beginning it goes down and eventually it turns up. So you might look at the first 30 terms and be like, oh, it looks like it's going down. Then all of a sudden later on it goes up. You have to see the formula to know, right?
Sorry, is that a sub n plus 1? Or
N
is it
plus
a
1.
Sub n plus 1.
This is a sub n plus 1 is down in the subscript. What this is saying is that, let's say we go to the, this is a sub 2, right? That's a sub 2. This one's a sub 3. So this one's one more than that, right?
Right.
This one needs to be bigger than that one for this to be decreasing, right? Or you can say it this way. This has to be smaller than that. So as you move through the sequence, the next one is always smaller than the one before it. That's what it means right there, right? You ready? This is the big part right here. I've got 10 minutes. This is usually the hardest thing to show. All right? You ready for this? I have to show that this is true. Don't know yet. So that means I have to take, what is a sub n? Well, it's n factorial over n to the n. Is that greater than? Is that greater than, what's a sub n plus 1? So what will be the one right after this one? It would be n plus 1 factorial over n plus 1 to the n plus 1. Please make sure you understand what I just did there, because we're going to be doing that a lot. I just plugged n plus 1 into that, right? That's all I did? Okay. I have to show that's true. It's not as bad as it looks. So what I'm going to do is this. I'm going to cross multiply basically. I'm going to take this and put it over here and take that and put it up there. Okay, so I have n plus 1 to the n plus 1 times n factorial greater than n plus 1 factorial times n to the n. Okay, so this is still a question. Is this true? Is that true? Is that true? Okay. Any ideas on what we could do? What does that become? You can peel off an n plus 1, and then you'd have that n factorial next to it, right? So if I do n plus 1 to the n plus 1 times n factorial, is that greater than n plus 1 times n factorial times n to the n? So all I did was rewrote this piece here. And what can I do now? Divide both sides by n factorial, basically cancel the n factorials out. There's kind of a little subtlety here. When I cross multiplied and I'm dividing through by n factorial, I thought on inequalities you had to be careful because sometimes they flip. They flip whenever you're multiplying or dividing by a negative number. And since everything I've been working with is positive, I'm not worried about flipping, right? Okay. All right, so let's take a look at that. Oh, does anyone else see what else we can do? Yeah, this n plus 1 right here, this side right here, this right here could be rewritten how? N plus 1 to the n times n plus 1, right? Because what you would do here, that's to the first power. If you put these back together, you would get this, right? But see I can peel one off, and that's actually going to allow me to cancel it with this one on the other side. Yeah?
Wait, what?
This right here, n plus 1 to the n plus 1 means n plus 1 to the n times n plus 1 to the 1. And then I'm going to be able to divide the n plus 1 out on both sides. So what's my next line? So my next line looks like this. N plus 1 to the n greater than n to the n. I think here we could probably say we're done. Because both sides are raised to the same power, right? And this base is bigger than that base. So that side should be bigger than the other side. If you wanted to go further, so I would be like at this point, I would say yes, okay? But if you want to go a little bit further, here's something else you could do. You could do n plus 1 to the n over n to the n greater than 1. So dividing both sides by n to the n. And then since these are both raised to the same power, you could put the power on the fraction. And this number right here is bigger than 1, right? That's bigger than 1? and 1 to the power, that's going to get bigger than 1, so that's bigger than 1, that's a check. Yes?
Could you take the natural log of n?
You could do natural log on both sides. If you do the natural log here and natural log here, then the ends pop out, then you can divide through, and then you have this. Right? You'd have that. Now this is true. Natural log is this what you were talking?
Base n of both sides. It'll just cancel
Oh,
together.
log base n.
Yeah.
Base n? Yeah, you could do it.
Can you get n
Yeah.
plus 1 greater than n?
Yeah. So I think there's kind of like we're there multiple ways here now, right? But you have to get to a point where you can't just at the very beginning be like, yeah, it's obvious it's monotonic. Like you have to show it's monotonic. Okay, that's it for this 8.1. It took us 2 days basically to get through 8.1, but we're done with 8.1. Make sure you do your homework for 8.1. All right, there's a couple of problems in there where they ask you to use the monotonic bounded sequence theorem to show that something converges, right?
Question, whatever.
Yeah, let me turn that off.